At last, we are finally here. The central parts of calculus, differentiation and integration. First, we go to differentiation. Without much build up, I'm directly going to define the derivative because you have probably seen it once or maybe even twice. Definition. Let I be an interval in R that is not a singleton. Let C be in I. We define f prime of C to be equal to limit x going to C f of x minus f of C by x minus C, provided the limit exists. Okay, so this quantity is called the Newton quotient. This f of x minus f of C by x minus C is called the Newton quotient. So if you want to summarize the definition of the derivative in as quick a time as possible, you just say it's the limit of the Newton quotients. Now you're already familiar with one particular interpretation of the derivative. Well, let's draw a picture. Say you have a curve. I focus on this point C. What I do is, again, I have a tendency of drawing these points somewhere in the air. So this is the point C. So essentially this will be C comma f of C. If I take a point X, then this would be x comma f of x. Okay. Now observe that this f of x minus f of c by x minus c is nothing but the slope of this line that passes through x f of x and c f of c. That's just this line. Okay, this doesn't look like a line at all. So let me try to draw that better. Somewhat better. Not considerably. Okay, so this blue line slope is given by f of x minus f of c by x minus c. That you're all familiar with from high school analytic geometry. So what is happening is, as this x traverses along this x comma f of x traverses along this curve and approaches the point c comma f of c, this line will start slowly turning, and finally at the point when you are at the limit, you will sort of get this tangent line to this curve at the point c comma f of c. Okay, so this is the familiar interpretation of the derivative as the limit of the secant slopes of the secant line. So let me just write interpretation 1. The derivative is the limit of the secant line, the slope of the secant lines, joining x f of x and c f of c. Consequently, it is the slope of the tangent to the curve at c f of c. Okay, so essentially what I'm doing is I'm considering the function as a graph. The graph is nothing but a curve. Then I'm looking at the secant lines passing through c f of c and x f of x, the line joining x f of x and c f of c, looking at the slope of those secant lines, and then as you move this point x f of x closer and closer to c f of c, these secant lines start moving and they become closer and closer to the tangent to this graph at the point c f of c. Finally, at the limit, it will in fact give you the slope. Okay. This is interpretation 1 that you are very familiar with from your high school studies. But this is not, in my humble opinion, the best way to look at the derivative. The best way to look at the derivative is to remember what it is used for. Okay. Why is the derivative so useful? The fact that there are calculus courses in every single university in the world should tell you something, that this notion of derivative is applicable everywhere. Why is the derivative so useful? And this slope business doesn't really answer this question, right? It's a nice geometric interpretation, but it's not clear why this slope of the tangent is so useful everywhere in all endeavors of human study. Well, let's rephrase the definition in a different way. First is this general principle that linear phenomena are easy. This is a general principle, not just in real analysis or calculus, but in the whole of mathematics. Linear phenomena are easy. Okay. Linear phenomena just means something that looks like a line. Okay. That's a very vague way of stating that, but essentially it's not such an imprecise thing as I make it out to be. So linear phenomena are easy. The derivative allows us to linearize a complicated function. In fact, when you study derivatives in higher dimensions, it's very common to call the derivative the linearization. Many authors do call it the linearization. What do I mean by the derivative allows us to linearize a complicated function? Well, let's look back at the definition. It's limit x going to c f of x minus f of c by x minus c. This is nothing but f prime of c, right? Note that this f prime of c is just a real number. It's just a real number. Okay. Now what I'm going to do is I'm going to forget this limit. Okay. Then I cannot write equal to. This will just be approximately equal to when x is close to c. Right? That's what limit means. As you get closer and closer to c, this will become a better and better approximation. Now, I don't know what an approximation means precisely, right? We are not in the habit of using sloppy language in this course. So what I will do is, instead of saying it's an approximation, I will say f of x minus f of c by x minus c is equal to f prime of c plus some error term. And clearly this error term will depend on x minus c. It actually depends on x, but it's actually better to say it depends on x minus c, because it sort of depends on how far away x is from c. Okay. So f of x minus f of c by x minus c equal to f prime of c plus e of x minus c. This is supposed to be the error. Now note, this expression I could have written even if the function is not differentiable. at the point C. I could have plugged in any number here, I can still find an error term, right? I just take the error term to be the difference of this and this. So I can always write this even if the function is not differentiable. When the function is differentiable, something very special happens, and let's see what that is. Well, let's take x minus c to the other side. So what we will get is f of x minus f of c is equal to f prime of c into x minus c plus the error term e of x minus c into x minus c. Okay. Now let's do some more algebraic manipulation. This is just f of x equal to f of c plus f prime of c into x minus c plus error of x minus c into x minus c. What has happened is we have got an expression for f of x. F of x is just the value at c plus this f prime of c into x minus c, which is certainly going to be linear. This part is linear, right? Plus an error term, error of x minus c into x minus c. Now note that if f is differentiable, so far all the manipulations I have done does not assume that f is differentiable. In the place of f prime of c, I could have put any real number and I would have got the exact same expression. I would have achieved nothing. If f is differentiable, note that calling this phi of h, note that limit x approaching c of phi of x minus c divided by x minus c goes to 0. Well, why is that the case? Well, let's just substitute phi of x minus c is just e of x minus c times x minus c by x minus c. X minus c and x minus c will get cancelled, and obviously as x goes to c, this error must go to 0. That's precisely the definition of saying that this limit f of x minus f of c by x minus c is in fact equal to f prime of c, right? So this error term goes to 0 as x approaches c. So what does that tell you about this? Well, we can write f of x equal to f of c plus f prime of c into x minus c plus phi of x minus c. Let us invent a new notation. Rather, it's already invented by Landau. Let's introduce a new notation that will allow us to summarize this expression that we have. Let phi from minus epsilon to r be a function. We say phi is little o of h if limit h going to 0 phi of h by h equals 0. Okay, so this little o notation, if you are a theoretical computer scientist familiar with computational complexity, this little o notation is used extensively there. It sort of measures the growth of a function. So what this essentially says is that f of x equals f of c plus f prime of c into x minus c. So this part is the linear approximation, plus little o of x minus c. This is the error, and the fact that it's little o captures that it is small. the error is in this particular approximation is not too large. That's captured by saying that it's a little o of h function. Okay, so the key fact is that the function, the error term is really small, and that's captured by saying that when you divide by h and take the limit as h goes to 0, you still get 0. That's simply saying that whatever this phi of h is, near 0, it is even smaller than h, right? Only then will limit h going to 0, phi of h by h be equal to 0. It will be much, not just smaller, it's much smaller than h, so that when you take the quotient, you still approach 0, right? Usually dividing by 0 leads to infinity, but that's not what is happening. You're getting limit 0. So that's sort of quantifying how small the error term is. So the upshot of our discussion is the derivative allows us to give a linear approximation of the function near the point C. Not only does it give you a linear approximation, it's a good linear approximation, which is captured by saying that the error term is a little o function. Okay, so this is pronounced little o. Little o. So this second perspective is what I will focus on in this course, that the derivative gives you a nice linear approximation of a function. So we have introduced the definition of derivative, and we have seen one geometric interpretation and one more algebraic interpretation in terms of linear approximations. As I have mentioned, we will focus on this second interpretation. This is a course on real analysis, and you have just watched the module on the definition and interpretation of the derivative.